Hello everybody, I'm Mark Tewksbury, your host for this program. Our goal is to reveal the materials and methods that turn out the everyday products we see around us. If you think you know something about these items, you might be in for some surprises. There's a whole world waiting for us to discover here on How It's Made. We all know butter comes from cow's milk, but did you also know that it can come from a camel? In olden times, when Arabs rode their camels, they hooked a goat skin filled with camel's milk to their saddles. The camel's ungainly walk stirred the milk, thereby liberating fat globules and forming butter. What a great idea. On today's show, steel, apple juice, aircraft landing gear, and cosmetics. Remember Superman? He could leap over a building with a single bound. He could also bend this with his bare hands. Bridges, skyscrapers, appliances, our lives revolve around this material called steel. Steelmaking usually begins with a pile of scrap metal. Using this 10-ton electromagnet, scrap iron composed of crushed car bodies, electric appliances, cans, and other steel scraps are gathered up. This powerful magnet is able to lift 5 tons of metal. About 83% of this scrap will be transformed into bars of steel. This metal is then dumped into a basket, which by itself weighs 32 tons. The basket can hold up to 60 tons of metal, and now they're going to melt the metal. This furnace reaches a temperature of 1650 degrees centigrade, hot enough to liquefy the metal. It is heated by 3 electrodes and by 4 natural gas burners. The contents of the basket are dumped into the furnace. Here, the pieces of metal come into contact with liquefied steel, which always remains at the bottom of the furnace. There's a reaction, and an aeration system draws out the smoke that's produced. At this high heat, the 60 tons of metal will melt in about 60 minutes. Then the cover is placed on the furnace. This liquid is composed of impurities, which rise to the surface when the metal becomes molten. At this stage, a workman draws a sample of steel to determine its chemical makeup. And now they make use of a supersonic oxygen lance. This lance blows oxygen into the molten steel, which reduces its carbon content, homogenizes the mix, and then speeds up the melting process. A ladle is positioned beneath the furnace. The molten steel will be transferred from the furnace into this ladle. The molten steel easily pours into the ladle. The ladle weighs 55 tons and holds 115 tons of molten steel. An overhead crane capable of lifting 180 tons carries the ladle filled with steel. Additives are introduced in order to obtain the correct steel tone. Here, the electrodes are taken out of the furnace ladle. A workman now opens the pouring nozzles of the distributor, equipped with 4 pouring holes. The molten steel runs into molds. It very quickly cools and begins to harden. Steel billets are produced in lengths varying between 4.5 meters and 10.6 meters. The billets are then cut to the desired length with a natural gas torch. A pouring identification number is marked on them with a wax crayon. The difference between a steel billet and the nearly finished flattened product is clear. Flattening of the billets remains to be done. Before flattening begins, billets are placed in the furnace to be reheated for 2 hours at 1095 degrees centigrade. Water jets cool the billet ejector. billets are placed on the flattener where powerful rollers compress them. This operation gives the billets the required shape and size. Water-cooled rollers crush the billets. Some billets go from a thickness of 12 centimeters down to 14 millimeters, while others reduce from 15 centimeters down to 19 millimeters. At the end of production, bars move along at a speed reaching 35 kilometers per hour. Once reaching their required dimensions, the bars must be cooled. This cooling bed allows the steel bars to cool uniformly. A total of some 400,000 tons of steel bars are made at this plant each year. Put thousands of these into a big press, apply literally tons of pressure, and what do you get? Apple juice, of course. Some people like me drink gallons of it every single year. Here at Rougemont, they make apple juice mainly from Macintosh apples. Some 90% of juice production is done at the harvest time in October. A conveyor transports apples to an inspection location. Apples tumble in the reverse direction of the conveyor belt so that wet leaves and undesirable materials adhere to the belt. The apples are stored in silos for several hours. In order that the apples are not too bruised in their descent, they're slowed down in this stepped chute. Juice making can now begin. Now they wash the apples. This first water bath eliminates pebbles since they also use apples that have already fallen from trees. A shower of cool water completes the washing process. The apples are then cut into little pieces in this grinder and produce gratings. Enzymes are added which break down the cellular structure of the fruit, allowing for maximum juice extraction. Next, the gratings are transferred into maceration reservoirs where they'll stay for 60 to 90 minutes. Then they extract the juice. The gratings are pumped into a powerful hydraulic press. Inside the press, filter sleeves hold back the skins, seeds, and stems of the apples. Quality control is strict. At each stage of the process, they draw off samples of juice to evaluate its quality and to make sure that fabrication parameters are well adhered to. The juice is filtered a first time. The very smallest undesirable particles are held back by this sieve. The fabrication process continues. Juice flows from one stage to another via these immense reservoirs. The next step will be pasteurization. Juice enters this exchanger at 22 degrees and is heated up to 88 degrees centigrade, then cooled back down to 50 degrees. Enzymes are then added to hydrate the pectin and facilitate the second filtration. This is the ultrafiltration process, where filter membranes with microscopic pores retain the smallest of particles. The apple juice is now perfectly filtered. Its clarity is verified, as well as its flavor, color, and natural fruit sugar content. Since juice is produced in October, it has to be conserved throughout the year. A portion of the production is stored in this sterile warehouse area to await being bottled during the year. Each reservoir can hold 110,000 liters of filtered juice. No preserving agent is added. Now we move to the next stage, which is the filling of the containers. These little drinking containers are filled at the rate of 100 a minute. The containers are then hermetically sealed. Two little sprays of hot glue are applied to the containers. This secures the straws attached onto their sides. Another automated production line fills bottles with juice. They circulate in a row on this conveyor. Bottles are washed and disinfected with hydrogen peroxide in this white sterile room. Then they're rinsed with sterile water before being carried to the filling location. Each minute, 120 bottles are filled with pasteurized apple juice and sealed with a cap in a sterile environment. Bottles are then labeled and sent to shipping. Between 20 and 40,000 tons of apples are transformed into juice yearly. Thanks to its perfect preservation, consumers can enjoy this juice at any time of the year. Flying is great, but easing hundreds of tons of aircraft onto a runway safely requires some pretty sophisticated landing gear. Let's see how it's made. This heavy piece of steel is the undercarriage of a KC-135R airplane. A landing gear comprises a central shaft to which an axle and wheels are attached. They begin machining the shaft. This digital lathe machines the exterior surface of the part. Sprays of water and oil cool the part, which heats up due to friction. They're now going to pierce the shaft. This drill head will remount the inside of the shaft. Alignment of the head must be perfect, so they're cautious with their work. The perforating gets underway. Turnings from the cutting are saved, and these will be sold to foundries where they'll be recycled. We see here the cutting tool used to pierce the holes in the landing gear. To perforate the part, very sharp cutting tools are used. Here, they complete an attachment hole. The hole is enlarged on its sides as required by this machine tool. The part is cooled with a mix of water and oil. Cutting is completed and the hole is now cleaned out with compressed air so that they can proceed with a visual inspection. Here, 3 pieces are rough cut at the same time by this machine. Because they'll be used in aviation, these pieces have to be machined to perfection. The machining of the shaft is now almost completed. This deburring unit polishes the machined surfaces with a compressed air tool and sandpaper discs. And now they have to verify the dimensions of the parts. This digitally controlled machine has 3 axes and does the verification with extreme precision. Here, another unit allows for the machining of parts with greater dimensions. This facility also reconditions used landing gear such as this one from a Boeing 707. They strip off the paint with a sandblaster to verify the condition of the parts with great precision. And here are those parts stripped clean. But a visual inspection is not enough. They can detect cracks by magnetic particle concentration. They magnetize the part and any cracks will become visible under ultraviolet light. Now it's time for the shot metal procedure, where they spray steel balls onto the metal surface to increase its resistance to fatigue. Before repainting the part, they first plate it. The part is immersed for 10 minutes in cadmium, which forms a protective coating on it that will resist corrosion. Then the part is quickly soaked in a weak concentration of chromic acid. Water, agitated by air jets, cleans away the chromic acid, and the part is rinsed with water another time. The part is now baked at 190 degrees over 23 hours to remove hydrogen induced during the plating process. Then the part is immersed in liquid nitrogen at -129 degrees centigrade before it's inserted in order to reduce its size. This collar is easily pushed on with a hydraulic jack. Reheating the collar makes it return to its normal size. Now the different components and the leak-proof joints are inserted into the piston. The shock absorber tube goes into the piston. This part absorbs the shock stresses when an aircraft lands. The piston is now slid into the cylinder, and they verify that the shock absorber is leak-proof. Fabrication finishes with paint baked in an oven. Some 6 to 8 months are required to make a new landing gear, and between 6 to 8 weeks to recondition a used one. When the old-time vaudeville comic shouted "makeup," he was unceremoniously smacked in the face with a giant powder puff. Today, we take makeup much more seriously. During archaeological excavations, mummies were discovered wearing makeup, the Egyptian technique of enhancing eye contours with antimony, lead, and metal oxides, all toxic, lethal substances. Greek women also adorned their cheeks with a dye made from lead oxide. In 1910, Florence Nightingale, under the name Elizabeth Arden, would change the whole makeup picture, launching the vogue for cosmetics without toxic agents. Cosmetics have been in existence since the dawn of time. There are many ingredients that make up a cosmetic formula. The industry heavily uses iron oxides to color its products in a multitude of attractive tones. Before moving into fabrication, each ingredient must be carefully and accurately weighed. These raw materials are often dry, such as powder, but can also be liquid, even oil or wax. Every ingredient will have first been approved by the Quality Control Laboratory. A single formula may contain over 50 ingredients. The other essential ingredient is water. The water used in making cosmetics is first purified by an inverse osmosis system. When it meets strict company standards, it is put into a stainless steel tank. Depending on the complexity of the recipe, between 4 and 10 hours of work are needed to make up a product. Let's begin with a bubble bath recipe. A part of the recipe is prepared in an adjoining container to make certain ingredients more soluble. A stainless steel screw propeller mixes all the ingredients thoroughly. All along its fabrication processing, the product will be subjected to many tests. Here, an acid-based neutralization reaction test is performed with a color indicator. The bubble bath has to be colored. A fragrance and a color are added, for in this recipe, the final product will be mauve. Before the filling process, the quality control and microbiology laboratories make sure that the product meets strict quality standards. Now it's on to the next step. This filler can simultaneously fill up to 12 700 milliliter bottles at a steady pace of 50 per minute. The fill level is adjusted electronically. Capping remains to be done. This capper positions and tightens the caps automatically. Urethane rollers apply the precise tightening force. The bottles now pass beneath a sealer via induction, which generates a magnetic field, heating the metal piece placed in the cap. When hot enough, it welds itself onto the neck of the bottle. Another product made here is the peeling mask. The mask is poured into this funnel, whose end is attached to the tube filler pipe. The product descends via gravity. The filler pours the peeling mask into 50 tubes each minute. Then, with heat and crimping, the tube end is sealed, and the tube heads for packaging. Other products made here, cologne and eau de parfum. The liquid is drawn into the bottle by suction. This rotating filler operates with intermittent vacuum to fill 50 bottles a minute. Bottles are positioned beneath the 16 filling spouts, which seal their opening to allow for the creation of a vacuum which draws in the product. Now atomizer pumps are inserted, handling 2 bottles simultaneously, This machine seals the pump, securing it around the neck of the bottle. We see the white sleeve aligning the pump, while the gray one tightens the pump. Then there are the sprayers. This machine applies the spray stoppers and, with a hammer, presses them onto the pumps of the bottles, which are now finished. And one final product, roll-on deodorants. This machine fills 115 bottles a minute, handling 8 bottles at a time. A filling stem pours the product into the bottle, and here they place the roller ball at 115 per minute. Then the ball is lightly pressed into the cavity in which it turns freely. This plant makes over 1,200 different products and yearly sells 32 million items. If a picture's worth 1,000 words, I hope what you saw today speaks for itself. We wanted to take you behind the scenes to the world of manufacturing. I'm Mark Tewksbury. See you next time on How It's Made.
Today, on How It's Made. Three-wheeled vehicles. What you get when you cross a race car and a tricycle. Baseball bats. We'll cover all the bases to bring you this story. Artificial bonsais. How to fake a centuries-old botanical art. And trombones. We'll tell you all about the brass tactics. Three-wheeled vehicles were introduced in the 1990s as exotic concept vehicles. This one is like a motorcycle on steroids. It has what's called a reverse trike design, 2 wheels in front and 1 in the back. It hugs the road like a race car, yet is legal to drive through city streets. This vehicle goes from 0 to 100 kilometers per hour in just 4.1 seconds. No faster than a motorcycle, but it definitely turns heads. Production begins with 34 steel tube components that will form the vehicle's chassis. A worker places them in an assembly jig. This positions the tubes for welding. After clamping the components in place, it takes the worker about 4 hours to weld 68 different areas together. For efficiency, 13 of the larger, more complex structures are pre-assembled. The steel tubes measure 3.8 centimeters in diameter, but the metal itself is only 1.5 millimeters thick. They're like those used in the aviation industry, strong yet lightweight. This company uses a visual reference method to assemble smaller parts of the vehicle. Before starting, a worker places 80 components on a board with labels that identify them. This way, he's certain he won't forget any nuts, bolts, bearings, brackets, or horns. Using an electric crane, a worker hoists the vehicle's 4-cylinder, 152 horsepower, 1200cc motorcycle engine into the chassis, now tinted black. Using a pneumatic wrench, he attaches it with 6 bolts and 6 nuts. Here, a worker assembles the 50 parts that make up what's called the foot box. This includes aluminum clutch, brake, and gas pedals. The brake pedal is thicker to withstand more aggressive use. The vehicle decelerates from 100 kilometers an hour to 0 in just less than 29 meters. He coats part of the brake pedal with a liquid sealant so vibrations won't loosen it. Another worker then mounts 2 output hoses and 2 plastic reservoirs for brake fluid. The brake fluid must withstand heat of 343 degrees Celsius, 30 degrees hotter than what's required for most cars. This enables better engine performance. He installs the footbox onto the front of the chassis using 3 bolts. Controlling the speed with the footbox is crucial, since top speed for the vehicle is 230 kilometers an hour. Next, he installs part of the suspension system, a cylindrical gas shock absorber. This attaches to the brake system, which is a zinc-plated rotor and an aluminum caliper. Then they attach what's called the 4-into-1 exhaust manifold. The 4 pipes merge into one to vent the exhaust fumes from the engine. They install the electric fan and radiator assembly. Next, a worker attaches a removable leather-covered aluminum driving wheel to the steering column. The driving wheel locks into place with a spring-loaded latch system. Just like a race car, you attach the steering wheel after you sit in the driver's seat so that you can get inside the vehicle. The collapsible steering column is part of the instrument cluster. This includes dials showing the vehicle's speed, mileage, and fuel. There are also switches for turning signals, hazard flashers, high and low beam lights, and to start and kill the engine. Next, workers install the rear wheel to another part of the suspension, called a swing arm. They attach it with 1 bolt that's nearly half a meter long and 2 smaller bolts. Workers then install a chain on the rear wheel assembly. When the vehicle's running, the chain's 94 links revolve on 2 sprockets to make the wheel turn. Rubber O-rings on each link prevent dust from damaging the chain. Finally, workers attach 19 molded fiberglass body parts. This factory offers 6 standard colors and several custom colors. When assembled, the vehicle is nearly 3.5 meters long, almost 2 meters wide, and just over a meter high. If you have a motorcycle license and a spare $50,000, you too can burn the pavement on this mean set of wheels. If you think a baseball bat is a pretty simple thing, well, you're out in left field. Making a bat means balancing things like weight and thickness. The material it's made of can make a difference. Metal bats hit the ball faster. However, the pros use wood bats because of league regulations, and even the type of wood might impact the score. Barry Bonds cracked a home run record in 2001 with a wood bat like this, one made of maple, instead of the usual white ash. They can never tell just by looking at it that a chunk of maple has what it takes to make a good bat. So they weigh it to make sure the wood is really as thick and heavy as it appears. Next, pointed prongs grip the wood and spin it, while a carbide cutter rounds it. This is a very modern lathe called an XY machine. The rounded blank goes into a room called the library, joining others on the shelf that are waiting for their chance at the big leagues. A worker selects one of the blanks to fill an order that specifies a certain model and size. He weighs it again to make sure it measures up to what the player has ordered. The blank goes onto the XY machine and spins. A computer guides the cutter as it moves on rails and carves into the blank. It whittles 2.5 centimeters of wood from the blank in order to form a handle. It takes a total of 3 passes on this cutter to make the rough shape of a baseball bat, but it's quick work, completed in just 3 minutes. Now it's time for another weighing in. The bat is substantially lighter, which is what they want. Next, he measures the end of a completed bat with a caliper. Using a square-edged scraper, he rounds the knob as the bat spins on a more traditional lathe. He measures as he cuts. With another caliper, he checks the thickness of a completed bat and compares it to the one he's just carved. Now he takes a turning tool called a skew chisel. With its pointed tip, he cuts into the bat's handle just above the knob to narrow the shoulder. Again, he measures as he cuts to make sure the diameter is just right. Using the skew chisel, he shapes the slope of the bat, repeatedly checking with the caliper to make sure it meets specifications. He slims down the handle a little more. Then he angles the top of the knob with the chisel. He shapes the rest of it with a square-end chisel. Next, he curves the bat's barrel using the same tool. This gets rid of sharp edges that would cause a ball's impact to ripple down and jar the player. Then he goes back to the knob and completes the shaping with the skew-end chisel. Because the tool is extremely sharp, he can carve very precisely. The bat is now within 14 grams of its final weight. Using an electric sander, he smooths down some of the rough edges. He switches to a finer grit to finish off the job. As he sands, he measures, because this isn't just about getting the surface smooth. The bat has to be exactly the right size and weight for the player it's being made for. Now he places the bat's knob in an end mill. A spinning carbide disc cuts around the holes made by the pointed grippers on the lathes, producing a gentle scoop. Next, a bigger disc carves into the barrel, cupping it. Some players prefer a cupped bat because it balances differently. Now he places the bat on the scale for the final weighing, and it's exactly what the player ordered. He brushes paint onto the barrel and rubs stain into the lower half of the bat. He presses decals onto the bat so it sports both the brand name and distributor. Then he stamps the model number in gold ink and tops everything off with a light coat of varnish. Now this maple bat is ready for the big leagues and some heavy hitting. Bonsai is a Japanese word that means plant in a pot. Growing trees in pots is a revered art that actually began in China more than 2,000 years ago. During the past century, creating artificial trees known as bonsai zoke has evolved into a hobby with global appeal. Whether it's rustic pine, flowering cherry, or Chinese elm, bonsai zoke can be made to resemble a variety of trees. Some include stones and small statues, a Chinese tradition known as penjing. A craftsman starts by wrapping 13 strands of wire with stretchy, sticky tape used by florists. He uses 13, partly out of respect for a traditional Asian preference for odd numbers. Later, these wires will form parts of the trunk and branches. He wraps the wires with strips of paper towel for thickness and flexibility. To hold the paper towel in place, he wraps the ends of the wires with more floral tape. He then separates clumps of plastic pine needles from their branches. Ironically, this fake vegetation is imported from China. Next, he snips off the ends of the branches, creating segments about 2.5 centimeters long. To reinforce and support these segments, he wraps them with tiny wire that's 0.5 millimeter in diameter. Next, he wraps the segments with floral tape to give them a more natural, branch-like appearance. Then he inserts these segments into the pine needle clumps. The thicker end becomes the bud and holds the clump on the segment. The craftsman now places 3 of these leafy segments together and attaches them with wire. He bends them sideways in the same direction. This mimics the tendency of natural branches to lean towards the sun. For more mature-looking buds, he uses different 3-headed artificial segments. For integrity, 2 different types of buds are never used on the same tree. To add character, the craftsman uses a piece of weathered driftwood as the base of the trunk. He anchors the long wrapped wires into styrofoam around the bottom of the base. He staples the wires to the driftwood and wraps floral tape around the wires surrounding the base. Then he twists the wire to form a sinuous shape, what the Japanese call moyogi. He covers the trunk with soft gray modeling clay, adhering closely to the shape of the driftwood underneath. This will later be covered by artificial bark and moss. This process can take several hours, just part of the 4 to 6 days it takes one worker to make a bonsai zoke. The craftsman then applies slow-drying glue to one side of strips of rice paper. The strips are 5 centimeters long and 2.5 centimeters wide. He uses about 50 to cover the trunk, like bark on a tree. He dabs them with a wet rag so that the creases will remain when the glue dries. The creases make the bark look realistically aged, one of the hallmarks of a good bonsai zoke. Craftsmen are careful to place the branches in the traditional triangle shape. The lower branches must droop, as if weighed down by the elements. They add the leafy segments to the ends of the wire branches, attaching them with wire and floral tape. Using a knife, the craftsman trims away the excess styrofoam around the tree trunk. He then places the tree into an argile pot that's 22 centimeters in diameter and 5 centimeters high. Using a sculpting tool, he covers the styrofoam in the pot with brown modeling clay. Using slow-drying glue, he covers the clay in several shades of fake moss. They range in color from dark brown to light green. He doesn't let the glue dry between each layer because the blending of moss and glue ensures a more natural-looking ground cover. He gently blows on the moss to scatter it across the base. He also applies glue further up the trunk, adhering moss that's thicker and lighter in color to resemble lichen. The finished bonsai zoke is 45 centimeters high. It needs none of the constant care required by its natural twin. Depending on their size and complexity, artificial bonsais range in price from $50 to $800. The adage, "it's hard to improve on a good thing," certainly applies to the trombone. The modern trombone isn't really much different from its medieval predecessor, known as the sackbut, with its distinctive S-shape, hand slide, and bell section. It's a blast from the past, and a pretty loud one, but it can also sound smooth and mellow. The trombone literally slides down to the low notes. It's the only instrument with a hand slide to lengthen it in order to change pitch. To make a trombone, they cut sheet brass in the pattern of a bell stem. They shape it by wrapping it around a steel rod. Using a nylon-headed mallet, the worker hammers the brass to shape it further. It takes just a few minutes for him to hammer out a rough bell stem form. He spreads open the stems slightly so he can make small notches on one edge with snippers. Then, with a brass-headed hammer, he taps down the notches so they hold the edges together. With an acetylene torch, he joins the notched seam, melting in a brass alloy wire to bond it securely. But the seam overlaps and it's too thick, so he runs it through a seam roller. 2 tons of pressure thins it. But now the bell stem is too flat. To round it out, he shoves it onto a bell-shaped rod and hammers it back into shape. Then he irons out the hammer marks with rollers. The bell stem, fitting loosely on a steel mandrel, goes through a draw bench. A hydraulic cylinder pushes it through a thick lead washer, pressing it tightly around the mandrel to its shape. To make the bell flare to attach to the stem, he puts a brass disc on a spinning lathe. Using pliers, he turns the edges of the disc to prevent it from flapping while spinning. With a lever, he manipulates a scissors spinning tool, pressing it against the turning brass disc. This shapes the disc into a flare. Making a trombone flare is a delicate business and is the work of a skilled craftsman. Getting it right is critical because the shape will affect the tone of the trombone. Next, with a torch, he braises the flare to the bell stem. The bell stem and flare now turn on a mandrel, while he presses against the seam with a wooden tool. This flattens the seam and gives the bell its final shape. Now it's time to make the tubing. A hydraulic cylinder pulls it on a mandrel through a die, stretching it considerably. In this way, both the diameter and thickness of the tubing are precisely controlled. Then, they become ice tubes, after they're filled with water and put in the freezer. The ice will keep the thin tubing from buckling in the next process. With a lever, he bends the tube around a U-shaped block. As he works it into a U-shape, the tubing hardens. After the ice melts, he places the U-bend in a balling out die. He lubricates the tubing with oil and places a steel ball at the top of the tube and presses it down. He drops in smaller balls and they push the first larger ball through the U-tube. This stretches the inside of the tube, rounding it to the correct diameter, and then the balls exit at the other end. Now he pieces the tubes together and solders them the same way a plumber joins copper tubing. He adds a loop for the valve section. In total, a bass trombone has 2 3/4 meters of tubing. Straightened, that's enough to reach from the floor to the ceiling. But of course, trombone makers are more interested in musical highs and lows. Finally, he solders a brace into place to add structural strength to one of the loops. A diamond-tipped tool engraves the company logo onto the trombone's bell stem, and a cloth buffing wheel spins against the trombone flare to polish it. This custom trombone has been built in approximately 50 hours, something worth blowing a horn about. If you have any comments about the show, or if you'd like to suggest topics for future shows, drop us a line at www.howitismade.net.
Today on How It's Made: carpets, drinking water, laser eye surgery, and acoustic guitars. People use the words rug and carpet interchangeably, but they're not the same thing. A rug covers just part of the floor. A carpet goes wall to wall. Today, most carpets on the market are made of synthetic materials. The first step is to make the carpet yarn. They start by feeding bales of nylon or polyester fiber into the opening and blending machine. The carding machine then untangles the individual fibers, lining them up in neat rows, then gathering them into wider bands. The bands go into cans. From the cans, they go into a machine called a drawing frame, which draws out 5 threads to make one rough, loose thread. That thread goes on to spools. Then they twist threads from 2 spools to make a stronger and thicker thread. Next, they twist 2 of those threads together to form a 2-ply yarn. To ensure the two plies don't untwist, the yarn goes through a heat-setting machine at 132 degrees Celsius. The continuous heat permanently sets it, much the way a curling iron sets hair. After 45 seconds of heat setting, the yarn is rewound on spools. Those spools then go to the tufting department, where the carpet making begins. A standard 144-inch wide carpet is made from 1,440 spools of yarn. Each spool feeds into a plastic tube, which feeds into the tufting machine, where the 1,440 lines of yarn feed 1,440 tufting needles. The needles stitch the yarn into a canvas backing made of polypropylene. With slow motion, you can see the yarn being hooked onto the canvas, then cut underneath into carpet pile. Up to 12 needles work each inch of canvas. The result is a pile carpet in the standard 12-foot width. Next, they dye it. For multicolored carpets, they use a machine called a chromajet. It works much the way a computer inkjet printer does, forcing streams of dye in different colors into the carpet fibers. The more complicated and colorful the design, the more often the machine passes over the carpet. For solid color dyeing, there's a mixer in each dye reservoir to keep the color even. They soak the carpet for 4 hours in a hot bath of dye and water, heated to 100 degrees Celsius. Another method uses heat and air pressure in an autoclave. What the bath method does in 4 hours, this method does in just 30 minutes, and with more carpets at a time. Once the dyeing is finished, they apply a water-based glue to a polypropylene backing. Then put the backing over the original canvas backing, locking the carpet fibers in place. Then it's onto what's called the marriage roll, a roller press that marries the two backings together. After a quick run through an oven to make the water and the glue evaporate, they cut the finished carpet into rolls. A standard roll is 30.5 meters long. Canadian researchers have invented a pollution-free car that runs on hydrogen. The research team modified the standard car engine to burn hydrogen instead of gasoline. Now they have to figure out how to prevent the hydrogen tank from blowing up in a collision. Drinking water that's fresh, clean, and crystal clear is something many of us take for granted. We might not give it a second thought, but between the source and our tap, a lot happens to make that water fit to drink. Our water may come from Mother Nature, but it's far from pristine. It starts its journey to the treatment plant through a water intake pipe. On the wall of that pipe, about 2 meters down, is a 15-centimeter hole. Covering that hole is a metal grill designed to keep out large debris such as tree branches. The water flows to a pumping station where it goes through a preliminary screening. A giant revolving screen removes fish, garbage, and grass. Once they remove the debris, a low-pressure pump moves the water into the treatment plant. The untreated water, called raw water, is dirty and smelly. So they first add a powerful form of the chemical element carbon, called activated carbon. It absorbs contaminants such as solvents and pesticides. That rids the water of bad taste and odor. From there, the water then goes through a series of mixing tanks. The first tank holds a chemical called aluminum sulfate. It acts as a coagulant, a substance that thickens liquid into globs. In the raw water, the aluminum sulfate forms tiny sticky globs called flocks. Bacteria, mud, and other impurities stick to those flocks. Then the flock-filled water moves on to the second mixing tank. The second tank holds a chemical called polymer, which is essential to the next step of the process, called sedimentation. 5 pipes inject the water with superfine particles of sand called microsand. The polymer coats the sand, making it sticky. The grains of sand then stick to the flocks in the raw water, weighing them down even more. The water then flows into a settling tank where the flocks, because they're heavier, settle to the bottom. You can see the result in this demonstration. The water is finally clear, but it's far from drinkable because it's still full of bacteria, viruses, and other organic matter. So on to the next step, filtration. The water flows onto the top of the filter, then trickles downward, passing through a layer of anthracite, a type of coal, then through a layer of sand. This filters out any remaining particles, which then flow to the middle. But the water is still teeming with bacteria and viruses, so it has to be disinfected. They add 1.9 milligrams of chlorine per liter of water, enough to kill off those germs and bugs. They add a mineral called silicate to prevent calcium buildup from blocking our water pipes. The treatment plant sends water samples to government inspectors who continuously monitor the water supply to ensure it meets safety standards. The amount of chlorine remaining in our drinking water is 0.6 milligrams per liter. The chlorine gas the plant uses is highly toxic. Should any leak out, emergency teams would have to evacuate a 10-kilometer radius. So the plant stores the drums of chlorine in a high-security area. It's taken about 45 minutes to turn raw water into treated water. Now these electric motors will pump it through underground pipes right to your tap. Short-sightedness, far-sightedness, and astigmatism are all due to light not focusing precisely onto the retina. Surgeons can correct this by using a laser to reshape the curvature of the front surface of the eye, called the cornea. The surgeon operates on one eye at a time. He cleans the eye, the lid, and the lashes with antiseptic, and administers anesthetic drops to freeze the eye and lid. He opens the lid wide with a speculum, then rinses the eye with a saline solution. Everything's frozen so the patient doesn't feel a thing. Next, antibiotic drops to prevent infection. Before every operation, the surgeon tests the equipment. He fires the laser on a metal plate to test its energy level. The surgeon administers a few more anesthetic drops, then inspects the microkeratome, the device he'll use to lift a very thin layer from the outer surface of the eye. He also measures the patient's cornea using an ultrasonic instrument. The cornea must be a minimum thickness for it to be safely reshaped. The surgeon uses the speculum again to prop the lid open. Then he begins the operation. He marks the eye with sterile ink, reference marks he'll use later. Next, he positions a metal ring around the cornea. The ring is attached to a suction pump so it clings to the eye. Like holding a tomato steady while you slice it, It holds the eye steady while the surgeon cuts the tissue. The surgeon lubricates the eye with sterile water, then mops up the excess water with a small absorbent sponge. Then he takes the microkeratome and slips it into grooves in the metal suction ring. In a matter of seconds, the device moves across the eye, cutting open a flap of tissue, the same way a carpenter's plane shaves a layer of wood. The surgeon uses a sterile sponge ring to keep tears from contaminating the cornea. He folds back the flap of tissue, exposing the cornea. He mops up the excess liquid, then starts up the laser. Meanwhile, a tiny sponge keeps the flap moist. The laser, an invisible light, fires in pulses, 50 pulses per second. Each pulse vaporizes a 1/4 micron of corneal tissue. The laser has been computer programmed beforehand, so it knows exactly how to reshape the cornea to give most patients 20/20 vision. In less than a minute, it's done. The surgeon removes the sponge and then, using those little ink marks he made earlier as reference points, folds the flap back to its original position. If the flap isn't precisely where it was before, the patient will have distorted vision. Using a syringe that flushes the area with sterile water, the surgeon carefully smooths the flap, the same way you'd smooth out a tablecloth. Then he removes the sponge ring. Within 45 seconds, the negative pressure inside the cornea sucks the flap back on. The flap literally seals itself. With the sponge, the surgeon dabs up any excess water. He applies antibiotic drops as a preventive measure, then inspects the microkeratome again before moving on to the other eye. He takes the speculum off, tapes the eye closed, then performs the same operation on the other eye. When that's done, the surgeon uses a high-powered microscope to make sure the flaps are wrinkle-free. The patient wears protection shields until the next morning, then overnight for a week. The best guitars come from trees about 800 years old, trees with enough rings in their trunks to provide wood with a tight and straight grain, wood flexible enough to vibrate, yet strong enough to withstand the pull of the guitar strings. The guitar traveled from North Africa to Europe with the Moors, who invaded Spain in the 8th century. In time, the guitar became the signature instrument of Spanish flamenco music and the trademark of the singing cowboy. In the 1930s, the acoustic guitar debuted as a jazz instrument. By the 1960s, as the electric guitar took over rock and roll, the acoustic guitar remained a staple of the folk music scene. They use spruce or cedar because those woods are lightweight and vibrate well. Using a 30-ton press that works like a cookie cutter, they punch out the shape of the guitar. The size of the sound hole affects how the guitar will sound. The larger the hole, the more treble. The smaller the hole, the more bass. Then they glue on a wood inlay decoration called a rosette. Next, they make the sides of the guitar. They first immerse wood pieces in boiling water for about 15 seconds. Then place them in a heated press to make the curve. The press applies heat from both the top and the bottom for about a minute. Then they connect the two sides with blocks of wood made of either mahogany or poplar. One is glued and clamped at the bottom, the other at the top. Then they glue on and clamp a wooden lining which will connect the sides to the top and back. Those little cuts give it flexibility around the curves. Then with a hand router, they carefully notch the lining to receive 4 wooden braces to support the back of the guitar. Strategically placed braces help the top of the guitar withstand the tension of the strings. They also equalize sound frequencies by controlling vibration differently at different spots. After a vacuum press makes the bracing adhere evenly, they glue on the top and bottom. The body of the guitar is now assembled. It goes into a press, then a drying rack for several hours. Next, they glue on a plastic binding to protect the guitar's edges. Then comes a fine sanding. Next, a machine with a special sensor measures the precise angle at which the body and neck of the guitar will later be attached. The angle is critical for sound quality. It drills the holes and sands the pieces accordingly. Next, they apply lacquer, 4 to 8 coats depending on the finish. The fingerboard is made of rosewood or ebony. The metal frets separate the half tones on the musical scale. An adjustable rod goes inside the neck. This lets the neck adapt to the different tensions that different types of strings require. They glue the fingerboard on the neck, then vacuum press it to make sure it adheres evenly. Next, they install the machine heads on which the strings will be wound. The rod in the neck slips into a groove on the body. The neck is then bolted and clamped until the glue dries. Next, they glue on the bridge, securing it with temporary screws and a clamp. Then they glue on the headstock nut, a hard plastic piece that spaces the strings evenly. Next comes the saddle, then the bridge pins which lock the strings in the bridge. Finally, they string the guitar using an electric winder. Because of all the glue drying time, it takes 3 weeks to make a guitar. The wood will become suppler the more the guitar is played, so as the guitar ages, the better it will sound. If you have any comments about the